Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about Lewis structures. We're going to talk about the steps you need to take in order to draw a Lewis structure, how to assign formal charge so we can optimize the best Lewis structure, as well as the exceptions to the octet, which there are a couple of. So let's get into this video. So the first thing we're going to do is we're going to talk about how to draw Lewis structures. So there are 4 steps in order for us to draw Lewis structures that are important for all Lewis structures. So you need to have a compound, and in this example we're going to use phosphorus trichloride. So the first thing you're going to do is you're going to count up all of the valence electrons that would be within this compound. Phosphorus has 5 valence electrons, and each chlorine has 7 valence electrons, and there are 3 of them for a total of 21. So 21 plus 5 is 26 dots or electrons that we're going to need to assign in our Lewis structure. So after you've counted up all your valence electrons and you basically put them into a pile, we have our 26 dots in a pile. The next thing you're going to do is you're going to draw a skeleton structure. So the way that you're going to do this is you're going to take the least electronegative element. And remember, the most electronegative element of all of them is fluorine, and the trend goes left to right, increasing electronegativity across the periodic table. So phosphorus is our least electronegative element, and it's going to go in the middle. Then what's going to happen is the most electronegative elements are going to surround the weaker one and start trying to rip its valence electrons away so that they can complete an octet. So the basics of what we're going to do here is we're going to have our phosphorus, and we're going to draw one bond or one stick between phosphorus and each chlorine. So therefore we've used 6 valence electrons, so we have 20 dots left to assign on this Lewis structure. So moving on to step 3, what you're going to do is you're going to decorate all of the outer elements, the most electronegative elements, with dots in order to complete their octet. Looking at chlorine, chlorine already has 2 shared electrons between each phosphorus and chlorine. So each chlorine would need an additional 6 dots to reach an octet, or a noble gas configuration of 8. So if we sprinkled on 6 dots to each chlorine, we would use 18 more dots, leaving us with 2 remaining electrons. So the last step, or step 4, is going to be to complete the octet on the central atom if possible. And we've got 2 dots missing on phosphorus. We've got 2 dots remaining in our pile. So we're just going to dot that phosphorus on there to complete this structure. And if we count all of the electrons in this structure, we have 26, as well as each atom in phosphorus trichloride has 8 electrons around it. So this is the best Lewis structure for this compound that we have. Sometimes it can happen though when you're drawing Lewis diagrams that you run out of dots and not everything has completed an octet yet. So if we look at this example, carbon dioxide has 16 valence electrons total. And if we were to draw a skeleton structure and assign dots just like I've told you, you're going to run out of dots. Each oxygen would have 8 electrons around it, but carbon would only have 4. In that case, when you run out of dots, you need to start shifting lone pairs from the more electronegative elements into bonds between those 2 atoms. So you're going to need a second bond between each carbon and oxygen in order to get carbon to have 8 total valence electrons without creating or destroying matter. So therefore, you can have double and even triple bonds in your structures if you run out of electrons. So the next thing we're going to need to talk about is what happens if your compound has multiple correct Lewis structures based on these 4 to 5 rules, and how will you know which one is the best? Well, then we're going to assign what's called the formal charge. The formal charge, the way you calculate this is you take the total number of valence electrons that an element has minus 1 dot for it in the structure, as well as minus 1 for each bond to that element within the structure. So if we have these 2 possible outcomes or scenarios for carbon dioxide, one in which we have a symmetrical compound and one in which we have a triple bond going to oxygen to the carbon, as well as another one with an oxygen with a single bond going to carbon. Well, let's figure out which one of these structures is the best. Let's calculate formal charge on each one of these atoms. If we're looking at the symmetrical compound, oxygen has a valence electron number of 6, and it has 4 dots, so we're going to subtract 4, and then it has 2 bonds to it, so we're going to subtract another 2. So 6 minus 6 is 0, and that value is the best that you can possibly get when you're trying to assign formal charge. You want your charge to be 0 if possible. If we're looking at the carbon in the middle, carbon starts with 4 valence electrons minus the 4 bonds. It has no dots, so it's 4 minus 4, so its formal charge is going to be 0, and then the other oxygen is symmetrical, so it's going to be 0. If we look at the other structure, the unsymmetrical one, let's look at the oxygen with the triple bond. The oxygen with the triple bond starts with 6 valence electrons. We're going to subtract the 2 dots, so that's 4, and then we're going to subtract another 3 for each of the bonds. So we have a +1 charge. This is a big indicator that this is probably not the right answer because oxygen is very electronegative, and only when oxygen is with fluorine would oxygen have a formal charge of a positive thing. That means something is pulling electrons away from that oxygen. And carbon is not strong enough to pull an extra electron away from oxygen. It's not going to be very stable. If we look at the carbon in the middle, our formal charge is 0, just like the one before, because it's 4 minus 4 for each of the bonds. If we look at the other oxygen, it's 6 minus 6 dots minus another 1 for the bond, so it's 6 minus 7 for a total of -1. This would be acceptable when we're trying to assign formal charges, as this is a -1, but this structure, the original structure, the symmetrical one, has all zeros, so this is the best optimized Lewis structure based on formal charge, and this is the one that we're most likely going to observe in nature. So the formal charge is a way to check Lewis diagrams to see if you can actually see these in nature or not. If you have to have Lewis diagrams that have a formal charge and you can't get them all to be 0, like in this set of 3 of thiocyanate, we're going to have 3 possible correct Lewis structures, but we're going to have a negative formal charge in one of these atoms. So let's see which one is the most electronegative. Nitrogen is the most electronegative element, so if we have to assign a formal charge of -1, it should be on that nitrogen atom in thiocyanate. Even though this overall charge is -1, we're going to have a -1 formal charge in nitrogen, so those match up. So we can't get them all to be to 0, so this is going to be the best formal charge based on your 3 possible Lewis diagrams. The next unique thing that we have is this idea of resonance. And resonance is the movement of electrons within a particle, and you may have 2 Lewis structures that seem to be identical, but they're really not. So if we're looking at this structure of ozone, O3 particle, we have a central oxygen atom with a double bond going to one oxygen and a single bond going to the next. So if we were to assign each of these oxygen a number, 1, 2, and 3, we've got the single bond going to oxygen 1 right now. So if we had another variation with the single bond going to atom 3, which would be correct, or which would we observe in nature? Well, this should be neither. We're going to observe neither of these in nature. It's going to be a combination of the 2. It's going to be a blending. So that double bond, those electrons in the double bond are going to resonate. So you're going to have a lone pair coming in from the single bonded one to form double bond, and then the electrons in the double bond are going to get kicked out to the next oxygen, and they're just going to oscillate back and forth or resonate between those 2 positions. So these are actually a 1.5 bond in reality. We could see if we actually take a spectrometer and measure where the electron density is, it's going to be clumped in the bottom, equally shared amongst both positions. So this is a resonance structure, and you may have possible resonance structures, and the true structure is going to be something in between. The other compound that's really important for resonance structure, especially if you go to take organic chemistry, is this ring called benzene ring. Benzene ring has a 6-carbon ring with 3 double bonds around the ring. You could equally draw this with the double bonds in the secondary position, but what's actually happening is those 6 valence electrons are oscillating amongst the entire ring. So they're all delocalized, and you basically have this ring structure that has very special properties. And if you go to take organic chemistry, your whole second semester is going to be focused on what you can do with benzene rings and all the decorations you can put onto them. So the last thing we're going to talk about in this video are the exceptions to the octet rule. So when you're drawing Lewis diagrams, you mostly want to get to octet, but some of these elements don't want an octet. They may want less or more. And there's 3 major categories for this. The first is if you have an ion or a molecule that has an odd number of dots. We call this a radical. And radicals are very unstable, so they're not going to last long having these single dots unpaired. So they're not going to exist long, as well as you're just going to assign the dots to optimize formal charge. The second more common one is going to be less than octet. And we know an element that we've been using all year, hydrogen, that doesn't want to take an octet. Its helium configuration is a noble gas configuration, and that's going to be most stable for hydrogen. So it wants to have 2 electrons just like helium. So this is less than octet. Another example of less than octet would be a boron compound. If we have something like boron trihydride, we've got 3 bonds for a total of 6 electrons around boron. If we were to calculate the formal charge on this boron, boron has 3 valence electrons, minus no dots, minus 3 bonds. So 3 minus 3 would be 0, and we could see boron having less than octet is more preferred for boron. The last category of the ones we mostly observe out in nature are going to be expanded octets, and these are going to be elements that can take more than 8 electrons around the central atom. The best rule for this is if it's in the 3rd period or below, particularly in the p block, you can expand the octet. And the elements that you see do this typically are sulfur and phosphorus. So if we had a compound phosphorus pentafluoride, phosphorus is going to take 5 bonds from each fluorine, expanding past 8 electrons. It's going to have a total of 10 valence electrons surrounding this central atom. Because it's in the 3rd period or below, it's acceptable to do this because they're going to have those shielding effects, which is going to allow more electrons available for bonding, as well as their atomic radius is larger, so it can accommodate more atoms around it versus a small atom like carbon or nitrogen. You're not going to be able to expand octet for those smaller radii. The last thing here is when you start to form double and triple bond, those are going to be stronger than single bonds. So the more bonds that you have between 2 atoms, the more energy it's going to take to split those bonds. Therefore, the stronger bond is going to be higher bond energy due to greater amount of bonds. So there it is, you guys. There's the video on Lewis structures, how to optimize formal charge, and the exceptions to the octet. So if you found this video useful, smash the like button, subscribe, send it to your favorite Plasmodium species, send it to your favorite ocelot, and we'll see you in the next video.